All right, here we go. So the first one should have looked familiar because that was the example I used on Thursday. And what you need to notice is that the epoxide here is on the less hindered face. You can actually redraw this. This is really a boat cyclohexane, where these are the two ends of the boat. So another way of looking at that same structure would be like this. And we avoid the transannular strain by having the two ends actually connected by a carbon. But there's still the eclipsing strain. So if you were to attack from the bottom, you have to work your way past these two axial hydrogens, whereas on the top you just have that one hydrogen that's kind of over the center of the bond. If you made these methyl groups, then the top face would be blocked and the bottom face would become the less hindered. But in this parent structure, because of the two hydrogens here versus just one on top, the top face is the less hindered. If we want an epoxide on the less hindered, that's the metachloroperoxybenzoic acid, and the usual solvent for that is dichloromethane. And remember, MCPBA looks like that, and it's got that peroxy acid where that oxygen there is the one that's the electrophile. Here we've got bromine and dichloromethane. That's an anti-addition of bromine. So all we have to do is decide whether it's the cis double bond or the trans double bond that's involved. These two bromines right now are on the same side of the molecule. So if we want this to be an anti-addition, we're going to need to rotate it and redraw this thing so that the other bromine is back. All right, so if we push that bromine back, that's going to cause these now to be on the same side. Oops, I just messed that up. That's the hydrogen. All right, so now these two are on the same side, so it should be the cis alkene that generates that product. Looks like a crab, two eyes up here. Zinc copper couple and diatomethane. This is the Simmons-Smith reaction. The source of carbon is the CH2I2. The zinc inserts itself into that bond, so you actually have an iodine CH2 and then zinc iodide. That's a carbenoid. So zinc iodide is going to eliminate, and this CH2 is what's going to insert into that pi bond, so the product will be the cyclopropane. You didn't really need to understand the mechanism to know that the Simmons-Smith reaction makes cyclopropanes. Here we have an electrophile on the sulfur. Sulfur is less electronegative than chlorine, so the sulfur acts as the electrophile, the chlorine acts as the nucleophile, and it's going to add across this pi bond so that the nucleophile ends up at the more substituted, and the electrophile, the S-phenyl group, ends up at the less substituted. That actually goes through an intermediate three-membered ring that has the sulfur looking like that, and then the chlorine opens, the chloride rather opens at the more substituted carbon where there's a larger partial positive. So we've added the electrophile to the less substituted and the nucleophile to the more substituted end. This is adding a dichlorocarbon, so what we need is the dichlorocarbene, and the way to generate dichlorocarbene is with chloroform and KOH. That's actually a good way to clean glassware too. The hydroxide takes off this hydrogen, then you have an alpha elimination to get rid of one of the chlorine, and this is so reactive it actually reacts with the glass surface and basically eats a layer of glass off and takes whatever stain is in the flask. You can only use it a few times before you run out of flask, of course. So those were two carbene reactions, one epoxidation, and two anti-additions of an electrophile and a nucleophile. Here we have another anti-addition of an electrophile and a nucleophile, but what's changed from the second reaction is that we've got water as the solvent, so the nucleophile is now the lone pair on water, the electrophile is still the polarizable bromine. And I've drawn this is a half chair here, you'll see. Because we've got this bicyclic bridge structure, there's hindrance at both the top face and the bottom face, which pushes it out of a chair and makes this part kind of planar on the right-hand side of the ring. Because of the methyl group here, the bottom face is the more hindered, which means the initial attack on bromine is going to be from the top face. So we're going to attack the bromine and push out bromide, and then one of these lone pairs is going to come in at the more substituted end. So step 1, right, is the electrophilic attack on bromine. And that happens at the less hindered top face to generate a bromonium ion. And that's a stereoselective reaction. It can attack at the bottom face, it just doesn't because the bottom face is significantly more hindered. So we have a bromine now. It's attached to both of those carbons. We got a methyl group on this side, hydrogen over here, 2 lone pairs and a positive charge. And now water is going to regioselectively come in from the bottom face at the more substituted carbon. So in step 2, the nucleophile attacks regioselectively at the more delta plus substituted carbon. Feel free to interrupt me if I'm moving too fast. Right? And stereo specifically, right, so it's regioselective, but it's stereospecific, anti from the backside of the bromonium. Because it hasn't actually left, right? It's like the epoxides where it hasn't actually left. So you still have it kind of hovering over the top. So that's going to leave the bromine on the top. On the end carbon, the methyl group is going to get pushed back up. And on the bottom, we're going to have an OH2 plus. Step 3 is simply a proton transfer, where we're going to generate the bromohydrin. Half the battle is actually drawing the molecule. So we have the OH down below and the bromine on the top. And now we go on to the second step with the aqueous sodium hydroxide to do the Williamson ether synthesis. So the bromine is here. The hydroxide ion is going to pull that hydrogen off to generate an alkoxide ion. So step 4 is another proton transfer. And now we have the O minus situated perfectly to where it can come in and do an SN2 reaction to kick bromide off, and now we've inverted the stereocenter where the bromine was. This is an intramolecular Williamson ether synthesis. And it goes SN2. So the first inversion of stereochemistry that happened when the water attacked is an SN1-like reaction. And then we have our epoxide down here. And if I want, I can redraw that in the planar form. I've got this methyl bridge on the bottom carbon, and now I've got the epoxide down on the more hindered, what was the more hindered phase. So it's the opposite result from the MCPBA. Any questions on that? So it's 5 steps, 2 points per step, and then 2 points for getting the product correct. Each of the others is just 2 points. So hopefully that was fairly straightforward, relatively speaking, once you get these 3-membered ring intermediate reactions down.